Hello and welcome to our presentation for the paper Sizeless Predicting the Optimal Size of Serverless Functions. So let's jump right in. What are serverless functions? With serverless functions, the development workflow is that a developer uploads his code and then sets up some events that he wants to trigger the execution of this code. The code is then executed on demand and with continuous scaling. Developers only pay for the time used with subsequent second metering. And a common sentiment here is that developers no longer need to think about resource management tasks. However, this is not quite true because developers are still in charge of resource sizing. Resource sizing is the task of selecting how much CPU, memory, I/O, bandwidth, network bandwidth, and so on are allocated to each worker instance. For serverless platforms, this is usually implemented as a memory size parameter, and the other resources are scaled accordingly with the memory size. And for the cost, this is calculated as the execution time multiplied by the memory size. And this is causing some interesting effects. I've brought a few examples here. There's two CPU-intensive functions here that invert the matrix or calculate prime numbers, whereas the ones on the bottom connect to a database or make a call to an external service. And what you see here is in blue, the execution time for varying memory sizes and the corresponding costs in orange. And if we look at the invert matrix function, we can see that the execution time drops rapidly with increasing memory size and the cost only increases slightly. Here, I would, for example, select either the 265 or the 512 megabyte memory size. For the prime numbers example, the execution time looks similar. However, since we have a super linear speed up here, we actually have a cheaper execution cost at 1.5 gigabytes. So this would, for example, be my preferred memory size for this function. When we look at the DynamoDB function, we can see that the execution time decreases pretty much linearly until 512 megabytes, where further increasing the function does not help. So I would select the 512 megabyte configuration here. And finally, for the API call, we can see that the execution time only decreases slightly when increasing the memory size. So here I would stick with the 128 megabyte configuration. So the takeaway here is that determining the optimal memory size of serverless function is important, but unfortunately also challenging. When we look at related work regarding the size of serverless functions, we first have a number of publications that measure the impact of memory size, and they all come to this conclusion that the memory size is an important parameter, but that's one that's hard to tune and it depends on the individual functions. Then we have a set of cost optimization techniques for serverless functions. These techniques mostly disregard memory size. And finally, we have methods that aim to optimize the size of serverless functions. And these methods tend to select and measure a couple of memory sizes and then interpolate the values for the remaining configurations. And what this means is that all existing approaches require to measure multiple function sizes. On the one hand, this is time intensive for the developers because they need to implement those tests. And it's actually impossible for cloud providers to use these techniques to handle the resource sizing because they cannot run performance tests on user functions. So the problem we're facing is that serverless functions still require resource sizing and that all existing solutions require the measuring of multiple memory sizes. And our idea here is that the resource consumption, so how much network, CPU, memory, and so on does a function use, should determine the impact of memory size. And therefore, we want to predict the execution time of all other memory sizes based on resource consumption monitoring of a single memory size. This would allow us to find the optimal memory size using only passive monitoring data instead of active performance tests, and it would enable cloud providers to handle resource sizing instead of pushing it off to the developer. So for our approach, consists of an offline phase and an online phase. In the offline phase, we use our synthetic function generator along with our resource consumption monitoring to generate a large data set where we have monitoring data for all memory sizes available. On this data set, we then train a regression model. And now for serverless functions in production, we can simply attach the resource consumption monitoring. From this, we get monitoring data for a single memory size. And here we can then use our previously trained performance model to predict the execution time for all memory sizes. And with this information, we can run an automated memory size optimization to provide the user with a memory size recommendation. So first, let's talk about the synthetic function generator. The idea here is that we want to generate a vast number of synthetic functions. And to do this, we implemented 16 different function segments that encapsulate tasks that are common for serverless functions, such as connecting to a database, reading, writing from a file, reading, writing to S3, managing images, and so on. And these function segments are then randomly combined to form a synthetic function. And this allows us to generate up to around 70,000 unique synthetic functions. So up next, for our resource consumption monitoring, we implemented this using a wrapper-style approach, and we monitor 25 different resource consumption metrics, which you can see on the right. And the important part here is not the individual metrics, but that they cover CPU, file system, memory, and network usage, as well as some Node.js specific metrics using the perfux library. So up next, we generated our data set. Here, to do this, we first randomly generated 2,000 synthetic functions. Next, we experimentally determined how long we need to measure each function until all metrics are stable. And as you can see here, the last metric becomes stable after 10 minutes. So this is what we choose for our experiment duration. And then we benchmark the 2,000 synthetic functions at 6 different memory sizes, which means we've conducted 12,000 performance experiments, which equals 216 million Lambda executions and about $2,000 in cloud costs. So finally, with this data set, we can now build our regression model. And the idea here is that for a function, we have as features the memory size that we measured at, the execution time that was observed, as well as the resource consumption metrics that we observed. And then as the target, so what the model is learning to predict is the execution time for all memory sizes. And then we have this for every function in our training data set, as well as every measured memory size. And on this data set, we then train a regression model where we also performed iterative feature selection and engineering, hyperparameter tuning, and the analysis of the ideal base size. If you want to know more about this, I would refer you to the paper. Something that I'll show here is our deep dive into the explainability of the model. So to find out how does the model come up with its predictions. To do this, we've used partial dependence plots. And what you see here is that for a observed memory size of 128 megabytes, so the smallest memory size, what speed up our model predicts when switching to different memory sizes. And then here on the x-axis, we have, for example, the parameter user time per second, so the CPU usage, and how that affects the prediction. And what we see is that if the function uses a lot of CPU, then we predict larger speedups. The same is for the case for the system time per second. When it comes to bytes received, so network usage, we see the opposite direction. So the more network usage, the lower is the predicted speedup. For the heap used, so the memory utilization, we can see that this only has a slight impact, but in general still correlates with speedup. And then when we look at other metrics such as file writes per second or the context switches per second, we can see here that there's no categorical influence, but rather that these features are used to fine-tune the model. And finally, let's talk about the memory size optimization. So when we want to find the optimal memory size, we're looking at a multi-objective optimization problem because we want to optimize for both cost and performance. Here we apply a pretty straightforward solution where we derive a score for the cost, which is the cost divided by the minimum cost, as well as for the performance where we have the execution time divided by the minimum execution time. And then these two scores are combined to a single score using a trade-off parameter, which is a common solution for multi-objective optimization problems. And now all we have to do is find the memory size that has the lowest total score. And we found the optimal memory size. So let's take a look at this in practice. We've evaluated this on 4 systems. The serverless airline booking, which models the booking aspect of an airline. And this was presented at reInvent. The event processing app, which models the processing of IoT events and was used in an academic migration study. The Hello Retail application depicts a prototype for an online shop and is shown by the retailer Nordstrom. Finally, the facial recognition application that, as the name suggests, provides facial recognition on images and is part of the AWS Wild Rights workshop. So for our evaluation, we've first looked at the question if our model, which we've trained on the synthetic data set, if you remember, can accurately predict the execution time of realistic functions. Here you see 3 examples, and you see in blue the observed execution time, and then here we see the crosses are the predicted predicted execution time for different base memory sizes. And you can see here that while it's not always spot on, the model very accurately captures the shape of the curve, so the impact of memory size. Where, for example, here it knows that there's a slight speed up expected here, and then no speed up here anymore. Overall, we have an average prediction error of 15.3% across 27 serverless functions. Next, we looked at if the execution time predictions are accurate enough to determine the optimal memory size. We've looked at this for 3 different values for our trade-off parameter, 0.7, 0.5, and 0.25. And you can see here that it usually selects the best memory size, often selects the second best memory size, and rarely the 3rd or sometimes 4th best memory size. But overall, our approach mostly selects the best or the second best memory size. Finally, we've looked at the benefits of using our approach. So do we get a cost decrease or execution time speed up? Again, we've grouped this for 3 different values of the trade-off parameter T, where this configuration focuses on or prefers cost savings, And we can see here that we have 2.6% cost savings, while at the same time speeding up function execution by 48%. And then once we lower the trade-off parameter, we see that their cost savings decrease, and we get a higher speed up. It's also the case here. You can see that the trade-off parameter works finely. And if we use it in our balanced configurations, our approach saves on average 2.6% costs, while at the same time speeding up the function execution by 40%. There's some limitations also to our approach. One is that the model that we've trained might become outdated. This can happen because cloud provider, in our case AWS, introduces new hardware or changes to their underlying software. What we can report here is that there have been 9 months between the collection of our training data and the last case study, and we could not observe any degradation in the prediction quality so far. Next, our approach doesn't really support multi-core applications at the moment because the model does not know if the application supports multiple cores, and it would therefore underestimate the expected speed up if it does. Finally, garbage collection. With garbage collection, the relationship between the available memory and the performance impact becomes more complex. And we could combat this maybe by also including garbage collection metrics in our model. We've also included a detailed replication package alongside our paper that passed the ACM artifact evaluation. And it consists of the performance measurements as well as our data set and analysis. For the performance measurement, we have fully automated the measurements. They only require the AWS access key as input, and they're wrapped in a Docker container for platform independent execution. So this allows the replication of the measurements of the synthetic functions as well as our case studies with a single command. For the dataset and analysis, we've published our measurement data that covers the execution of over 2 million functions, function executions rather. And it also includes the scripts to reproduce all analysis tables and figures from the manuscript, and we've wrapped this in a code ocean capsule, which enables the replication of this part with a single click as well. If I got you interested, feel free to check out our GitHub repository. To summarize, determining the optimal resource configuration of a serverless function is difficult. We propose an approach that trains on a synthetic data set in an offline phase, and then during the online phase requires only monitoring data for a single memory size in order to optimize the memory size, which enables the method to also be employed by a cloud provider. We've evaluated this on 4 case study systems, and in our evaluation, we've shown that we have a prediction accuracy of around 85%, select the best memory size in 80% of the cases, and can provide a speed up of around 40% while having slight cost decreases. Thank you very much for listening to this, and this concludes my talk.